Okay, good morning, everyone. We'll probably still have people zooming in the next 5 to 10 minutes. So I'm going to start off. Obviously, we're getting close to midterms. And as I mentioned, I'm actually a full-time professor over at Shepherd University, which is a state college or state university, rather, in West Virginia. And I'm on the adjunct faculty at University of Maryland. And I teach, I'm in the business department over at Shepherd University, and here I'm in the computer science department. And I teach a class similar to this idea of discrete mathematics in the business department over there. The course taught in business is known as finite mathematics. And it has similar topics, but they also go into slightly different ones. So I thought it'd be interesting for you guys to know kind of what the differences are. in the finite mathematics, they spend a good deal of time on linear equations, matrices, and what's known as linear programming, which is a constrained optimization. And we go into some detail in the simplex method for doing that. And by the way, the simplex method was actually developed by a professor in the math department at the University of Maryland in the late 30s. So we do spend some time on that. Similar to what we're covering, here's somebody, similar to what we're covering in our course, we do go into sets and logic, the truth tables, logical implication and equivalence, valid arguments, predicate calculus, and circuits. But then we also spend more time on things like Markov processes and the theory of games in finite math. In discrete math that the computer science folks take, instead of looking at the simplex method and Markov chains and the theory of games, we go into things like induction and recursively defined sequences. So those are things that we'll need in computer science. And we also spend a good deal of time on directed graphs that we don't in finite mathematics. Interestingly, directed graphs are now one of the ways of structuring data in databases. They're known as graph databases, and Neo4j is one of the leading NoSQL databases. It's actually a development and improvement over what had been known as hierarchical or network databases from the late 60s and into the 70s. And they were developed by another University of Maryland professor. This one from UMBC, Dr. Edgar Sibley was the chair of the IFSM department as it was known back then. And the network and hierarchical databases were actually acyclic directed graph databases. And so Neo4j and the more modern implementations of these directed graph databases are very similar in concept to what was originally done back in the 70s. So those are the main differences. We are going to have a midterm next Thursday. That's a week from today. It's going to be online. I will email it out to you. I'm in the process of finalizing it now, and then once I get that finalized, I'll work on a review that I'll send out over the weekend. And we're going to have a review session next Tuesday to go over what's going to be on the exam and the type of knowledge you'll be expected to know. So that will be next Tuesday. We'll have the review session, and then next Thursday, we're going to have the exam. It obviously is going to be online. Oh, that's interesting also. At Shepherd, all our classes are in seat at this point, whereas I don't know if at UMBC, I know this class is strictly online. I don't know if they actually have in-seat classes at UMBC yet, but the exam is going to be formatted as a series of questions or problems. Well, I was going to send it out at our regularly starting time of 10 o'clock, and then you finish it and send it back by 11:30. So that gives you some extra time, and that should be plenty of time to take it, especially as we go through the review. If you're comfortable with what's on the review, you'll be in good shape. Okay, so I guess this is it. We've got 18 people. Usually we're in the mid-20s. Let's go ahead and get started. If other people join us, that's going to be fine. So I'll go ahead and fire up my PowerPoint and share it. Okay, and today we're going to look at arguments with multiple quantifiers. So we have this concept of universal instantiation. And the idea here is, we deal with these quantified statements for all, or there exists at least one or some. And what we'll have is then we say, okay, we have that universal statement, but then we can have this idea of a universal instantiation where we say we have a particular element in our domain. And then based on that particular element, the universal property or properties that we describe in our premises hold for that particular instance. And that seems intuitive, but mathematical formulas, definitions, and theorems are like general templates. In other words, these for all x, or there exists at least one x, these are like general templates that are used over and over in a wide variety of particular situations. So you have a particular instantiation or element of this general principle that you're looking at, but the general principles hold for the specific element case. So we have the idea of a given theorem, and it says that some property holds true for a certain domain, certain elements for a certain domain, and that means it will hold true for the elements in that domain. So if you have a particular object that's in that domain, a particular element that's in that domain, then the universal rule applies, and we have this concept known as universal instantiation, where you can conclude that the general principle that holds for all of the elements in the domain hold for a particular element in the domain. So let's look at some examples of this. And of course, we're familiar with modus ponens and universal modus ponens. And here's a concrete example of what we're talking about. We've got this universal statement for all x. If x has the property p, then x has the property q. Or you could say it as for all x, if p of x, then q of x, or if x makes p of x true, then it makes q of x true. So that's our universal statement. Then we have a particular element in that domain, and we say p of a is true for that particular a. Then we can conclude that q of a is likewise true for that particular a, because it's true more generally in terms of this universal law that we were looking at. So the first or major premise is written: all things that make p of x true also make q of x true. And so then we have an instantiation as the minor premise. Well, p is true for this one element a, and then we can then say, well, then q is true for that element a as well. And typically we've gone over how we can word these things different ways, but the if-then form is more natural, especially in computer science, because we're used to seeing if-then type conditional statements in our programming logic. So let's take a minute and look at an example here of recognizing this universal. And in this case, we'll be looking at modus ponens. So take a minute, look at that, and then we'll go over it. We want to rewrite that using quantifiers, variables, and predicate symbols, and then look if it's valid or not. Okay, let's take a look at this. So we have the argument, if an integer is even, then its square is even. K is a particular integer that is even, therefore K squared is even. So the major premise of this argument is going to be, for all x, if x is an even integer, then x squared is even. So we can, devise some notation. So we could say something like E of x stands for x is an even integer, and S of x means that x squared is even. And then we can let K stand for one particular integer that's even. So then we get an argument of this form, and let me put it up on the board here. So we get an argument of this form. This is just a formalized view of that argument we see in the slide. For all x, if E of x, then S of x. In other words, if x is even, then x squared is even. Then we have the particular. One particular integer k is even. Then we can conclude through universal instantiation of the more general premise up here that S of k is true too. So if k is an even integer, then the square of k is even as well. This is a valid form of argument, and it's known as universal modus ponens with universal instantiation. Let's go back. Okay, let's look at how we might use universal modus ponens in a proof. So we might take this idea that two integers, the sum of any two integers is even. And so we can make use of this universal modus ponens. So we can say an integer is even if and only if it equals twice some integer. So we have more formally a statement, for all integers x, x is even if and only if there exists an integer k such that x equals 2 times k. So if we have two particular but arbitrarily chosen integers, m and n, and then we can say, well, m, they are even integers, arbitrarily chosen even integers. And we can say m is equal to 2 times r for some integer r, and n is equal to 2 times s for some integer s. So we get m plus n is equal to 2 times r plus 2 times s by substitution. Then by factoring, we get 2 times r plus s. Now, remember the sum of any two integers is likewise an integer. And so we get r plus s as an integer, and also then 2 times r plus s is an integer. But since 2 times r plus s is evenly divisible by 2, then that means m plus n is even. So more formally, we can write this out, and we take the first step where we say if we have an integer that's even, then it's equal to twice some integer. And that's our general statement. Then we have m is a particular integer, that's our instance. And then by universal instantiation, we can say m equals twice some integer r. And of course, we do the same thing with n and come up with the conclusion n is equal to twice some integer s. Then we say if a quantity is an integer, then it is a real number, because integers are part of the real number system. And so r and s are, of course, particular integers, and therefore r and s, through universal instantiation, are real numbers. So we can apply some of the rules of real numbers and say, okay, if we have numbers a, b, and c, then ab plus ac is equal to a times b plus c. So then we have this idea 2 times r plus 2 times s is equal to 2 times the sum of r plus s. For our fourth step in this formal proof, we then look at, we've got integers u and v. So u plus v is also an integer, and r plus s are then, so the first statement is the universal for all integers u and v. U plus v is an integer. And through instantiation, we say, well, r and s are particular integers. Therefore, through universal instantiation, the conclusion is true. The hypothesis is true. The conclusion is true. So we say that r plus s is likewise an integer. And then for the final step, we say we have the universal if a number equals twice some integer, and that number is even. Then we have the particular 2 times r plus s equals twice the integer r plus s. And then through universal instantiation, 2 times r plus s is even. This is the idea of universal instantiation. We have our major premise is a universal statement. And then we have, for our minor premise, a particular in that domain. And then our conclusion is going to be the consequence of the if-then statement. We have the hypothesis true, the conclusion of that statement will likewise be true for a particular. And this also holds for universal modus tollens. And this is another critical technique in mathematics, and it's used often in proofs by contradiction. So if you can prove that the conclusion Q is false, then you know that the hypothesis P is not true as well. And that, again, is one of the important forms of mathematical argumentation. So the formal version of it's going to be, again, our universal statement for all x, if P of x, then Q of x. That's the universal. And we have a particular. For a particular element A in the domain, Q of A is not true. Then by modus tollens, we can, and universal instantiation, we can conclude that P of A is not true either. So let's take a look at this argument and we want to rewrite it using quantifiers, variables, and predicates, and determine if the argument is valid or not. So take a minute and look at that one. Okay, let's take a look at this one. So the major premise can be rewritten more formally as for all x, if x is human, then x is mortal. So we can use a notation h of x to be x is human and m of x to be x is mortal. And then we can have a particular z, and that would stand for Zeus. Then the argument becomes for all x, if h of x, then m of x, not m of z, therefore not h of z. And let's take a look at this on the board. So again, our universal statement is for all x, if h of x is true, in other words, x is a human, then m of x is true, x is mortal. Then we have our particular instance, z. So Zeus is not mortal. Therefore, Zeus is not human is the conclusion. So we've written it formally like this. And then the question is that a valid form of argument? And it is, because it has the universal form of universal modus tollens, and therefore it's valid. Me back up. So it is a valid form of argument through modus tollens. Okay, let's look at how we prove the validity of arguments using quantified statements. So we say that an argument is valid if and only if the truth of the conclusion follows necessarily from the truth of its premises. So if we have particular cases where all the premises are true and the conclusion is true for all those cases when the premises are true, all true, then it's a valid form of argument. So no matter what particular predicates are substituted for the symbols in the premises, if the premise statements are all true, then the conclusion is also true. If that's the way it is for every case, then the argument is a valid form of argument. Let's look at a couple of ways we can test for validity. And one way we might start with is a visual technique by diagramming. And so we can use diagrams to help us test for validity at an intuitive level. So we might start with this universal statement: all integers are rational numbers. So we could say for all integers n is a rational number. So if we want to draw disks for representing integers and rational numbers, we would get something that looks like this. So the outer circle is rational numbers. All integers are rational numbers, so we have an inner circle of integers. Now, not all rational numbers are integers. So there's going to be some part of the rational numbers circle that does not contain integers. So we look at that and we say, okay, the integers is entirely within the rational circle. So we have these statements for all x in D, Q of x, and for all x, if x is in D, then x has the property Q. These are logically equivalent. We've talked about them. It's basically, in the first case, you're narrowing the domain down to the case where x is true for that domain. In the second case, you're looking at a domain of all x, and then you're looking at a subset of those if x is in D and Q of x. But they're logically equivalent statements. So we can test the validity of an argument with these diagrams, and then determine the validity by looking at the diagrams and the conclusion itself. So let's take an example of that. We want to use a diagram to show the invalidity of the following argument. All human beings are mortal. Felix is mortal. Therefore, Felix is a human being. So let's take a look at this diagrammatically. So spend a minute, go over this, and then we'll look at it diagrammatically. Okay, let's take a look at this one. So we have our major premise: all humans are mortals. So we've got our set of mortals represented by this outer circle. And then we have a set of humans, and all humans are mortals. So all humans are mortals, but it does not say that all mortals are humans. So there's mortals that, it's very possible there are mortals that are not human, represented by the elements of the circle mortals that are not within the circle humans. our minor premise is that Felix is a mortal. So it doesn't say we don't see anywhere that Felix is necessarily a human. It could be that we've got this situation. We have a circle humans here and a particular element Felix over here. We have no way of knowing this is not the case based on our minor premise. So we cannot conclude that diagrammatically that Felix is a human. So again, all that's known is that the particular element Felix is located somewhere inside the set of mortals or inside the mortals circle. Where it's located with respect to the human beings set or human beings circle, we can't determine from the premises given. So it's possible that Felix is a human being. It's also possible that Felix is a cat. So we can't rightly conclude that Felix is a human being. So we can look at some ways of perhaps if the argument were changed, we would be able to make it true. So again, if we take a universal conditional statement and replace it by its converse, that might make the particular argument we just looked at true. However, remember, the converse and the inverse are not equivalent logically to a universal conditional statement. A contrapositive is. So this is something that is exhibiting a converse error. And then we have another case. This is the inverse error. So in this particular error, you have something for all x, if p of x and q of x, then we have not p of x, a particular instance for the particular element a, p is not true. We can't conclude that it does not have the property q, even though a does not have the property p. That's an invalid conclusion, and that's an example of the inverse error. Okay, so let's take a minute. We'll look at this. Look at the particular argument here and use diagrams to test the argument for its validity. Okay, let's take a look at this one diagrammatically. So our major premise is that we have polynomial functions, and no polynomial functions have asymptotes. So these are the, this is the major premise. And then we have this particular function. So our particular function has a horizontal asymptote. So our particular function is in this circle with the functions that have asymptotes. So we can see that our function is not a function that's a polynomial function. It's not in any part of that circle. So diagrammatically, we get a more intuitive sense for what's of the validity of an argument. So again, a good way to represent a major premise is diagrammatically. So we have these two disks, polynomial functions, and then functions with horizontal asymptotes. And then the minor premise, which is going to be a particular element, you put that in the appropriate circle. So in our case, we put it in the circle that had functions with horizontal asymptotes. So that is our minor premise. And then you can tell diagrammatically if it's part of the conclusion or not. So again, the minor premise in this case is represented by placing a dot inside the disk with asymptotes. So the argument is valid. That function was not a polynomial function. And an alternative approach to doing this is to look for equivalent forms in our logical arguments. So we have a restatement of somebody, okay, oops, let me see here. Yes, it is. So yeah, if and we've gone over it, it's possible to have a valid argument, but the conclusion is not true. So yeah, that's definitely possible. Remember, the what we're saying is with these forms, if all the premises are true and the conclusion is true, then we have a valid form. We're not necessarily saying that we're going to derive the absolute truth out of it. So again, another way we could state this argument is that for all x, if x is a polynomial function, then x does not have a horizontal asymptote. And then we come up with our particular. So that's the universal. Then our particular is that for a particular element A, that element does not have a horizontal, it has a horizontal asymptote. So Q of A is that it does not have a horizontal asymptote, and therefore not Q of A is this one does have a horizontal asymptote. And then we can therefore conclude not P of A. In other words, A is not a polynomial function in this particular argument. So this is a valid form of argument. It's universal modus tollens. And we have a particular instantiation where we negate the conclusion, and therefore we have to negate the hypothesis. Now we can extend the concept to additional forms of argument. And so we've looked at modus ponens and modus tollens. And in the same way, additional forms of argument involving universally quantified statements can be obtained by combining this idea of universal instantiation with other of the valid argument forms that we've discussed in the past few weeks. Now, one of the common forms that we run into is something we discussed, and that is a transitivity. So we've got transitivity here. If P is true, then Q is true. If Q is true, then R is true. If P is true, then R is true. This follows from transitivity. So, let's take a look at this argument. So we've got three premises and we have a conclusion. So it is a valid argument. So let's write this in a formal notation and then arrange the premises. You can change the order of the premises without changing the validity of the argument form, and come up with a argument form where we can follow step by step whether or not this is a valid form of argument. And of course, it is a valid form of argument. So take about 5 minutes and go through this one. Okay, let's take a look at this one. So the first thing we want to do is rewrite these statements in formal notation. And that way we get an idea of perhaps one of the laws of logic that we've looked at the last couple of weeks that might apply to our particular circumstance here. So we have three premises and a conclusion. And we can write them formally like this. Premise one is that for all x, if x is a triangle, then x is blue. The second premise is that for all x, if x is right of the squares, then x is above circles. Then the third premise is for all x, if x is not to the right of the squares, then x is not blue. And from that, we have our conclusion, and that is for all x, if x is a triangle, then x is above the circle. So the first thing we want to do is we do have the right to switch the order of the premises to help us in understanding the flow of logic that might be the case. So we can get an equivalent form of the argument over here. So we'll keep the first premise in the first order. So our first premise equivalently is for all x, if x is a triangle, then x is blue. However, we're going to switch the places of premises 2 and 3. So we put premise 3 in second place and premise 2 in third place. So we can switch, in this case, 2 and 3 around. Now, the contrapositive of a statement is logically equivalent to that statement. So we can take the contrapositive of P3 and plug that in as well. So doing that, we get for all x, if x is blue, then x is to the right of the squares. Notice that we have if x is a triangle, then x is blue. Then this comes down here. If x is blue, then x is to the right of the squares. And then with P2, we get if x is to the right of the squares, then x is above the circle. So this is a form of transitivity. If P, then Q, if Q, then R, and therefore if P, then R. So we've got it here. This is transitivity. So if we start off with this, if X is a triangle, through transitivity, we come to this conclusion, then X is above the circles. So this is the idea of we can reorder premises, take the contrapositive of a statement, and try and get it into a logical form that we know to be a valid form. So we have to be careful, though. We cannot replace a statement with its converse or its inverse. But we can replace it with its contrapositive. Okay, let's look on this idea of converse and inverse errors. So a converse of a statement, if you replace that your original logical statement with its converse, that's not a valid logically equivalent substitution. However, and we've noted this earlier in the lecture. However, in practice, people will actually do exactly that, and it's a valid form of investigation. And the reasoning goes like this. If we have the case of, this is a converse argument. So for all x, if P of x, then Q of x, then we have the converse of the statement Q of A is true, then logically we can't say that we know that P of A is true, but it might be a line of inquiry that we want to follow anyway. And here's an example. So for a medical doctor, we have, the case. Here's a diagnosis for all X. If X has pneumonia, then X has a fever, chills, coughs, and is exceptionally tired and miserable. And then that's the universal. And then what we have is we have the conclusion true. So John has fever, chills, coughs, and feels exceptionally tired and miserable. So on the basis of that, even though it is a converse error, the doctor is going to investigate the possibility that John has pneumonia. It's not logically certain, but because there is that association, he's going to look into the possibility. So there's a possibility it's not the case, but it's a possibility that it is true. And therefore, the doctor will investigate that possibility. So this form of reasoning is known as abduction. And it's often used in expert systems in artificial intelligence. So the closer a set of symptoms in the case of a medical expert system, the closer a set of symptoms comes to being necessary and sufficient for an illness, the more certain a doctor will be of the diagnosis. But obviously they make a diagnosis and then they have to find corroborating evidence that increases the probability that they're right, because there's not a definite certainty in abductive reasoning. Okay, so today we've looked at instantiation. We have, like we've been covering the last couple of lectures, universal statements for all x, there's a condition true q of x. Then we have a particular element of x. Let's call it one element. So if that element is a, then we can say that q of a is true by universal instantiation. And we looked at how that follows and can be used in modus ponens, modus tollens, and transitivity. We noted that the converse and the inverse of a statement are not logically equivalent to the statement, but the contrapositive is. And of course, we've been saying that all along in logic, both in our predicate logic, in quantified statements, and again, here in the looking at valid forms of argumentation. So in all cases, we said that the converse and the inverse were not the same logically as the statement the contrapositive was. And we concluded with the idea that sometimes, however, in the field, people will do what's known as abduction. And even though it's not, the converse is not, a converse error is a logical error, they will pursue it on the basis of there's a probability, not a certainty, but a probability that it could be the case. And then they find corroborating evidence to support that reasoning. Okay, so again, I am going to finish up the midterm. I'll be posting over the weekend the review that we'll be going over on Tuesday. Tuesday, we'll have a review where we'll go over the knowledge you will need for the midterm. And then next Thursday is the midterm. I will email it out to you at 10 o'clock on Thursday, and then you'll email me the answer back at 11:30. So, see you on next Tuesday. Okay, thank you. Right, bye. Thank you. Have a good day yourself. Thank you. Thank you. Yes, the review will be coming out this weekend. I'm getting close to finalizing the midterm. Yes, today was lecture 11. By the way, I'll have lecture 10, which was Tuesday, and lecture 11 posted by tomorrow morning. I just got to put them on YouTube and then put my links from Blackboard over to YouTube. Okay, you're welcome. You're welcome. No, the midterm was always next Thursday.